Okay, 10.5 is testing convergence at endpoints. Okay, again, this is a very lengthy section. There's a lot of theorems, and I'll go through a few things with you. The first one is called the integral test. All that says is you let your some series AN be a sequence or a series of positive terms. And you suppose that A sub n equals some f of n, where f is continuous. Basically, this is what it's saying, that this series at n to some number to infinity, some series, and the integral from n to infinity, f of x dx, either both converge or diverge. If this is a series and this is the integral, if the integral converges, then the series converges. If the integral diverges, then the series diverges. So, for example, in the next problem, this integral at n equal 1 to infinity of 1 over n square root of n, it converges. I'm just going to give you an example. I'm going to start with n equal 1 here, n equal 2 here, n equal 3 like I've been doing. When I put 1 in there, I'm going to get 1 over 1 plus 1 over 2 square root of 2 plus 1 over 3 square root of 3, and so on. And you can see that these numbers are getting bigger and bigger, so all of these are getting closer and closer to 0. Since this has a limit, so does the integral. So if you take the limit as k approaches infinity of x raised to the negative 3/2 power from 1 to k, I got x to the negative 3/2 because this is n to the first and this is n to the 1/2, which really makes n to the 1 and 1/2. But if you bring it up, it's really x to the negative 3/2 dx. And when you integrate that, you're going to get a negative 2x to the negative 1/2 from 1 to k. And it's going to get closer and closer. It's just going to converge. Because whatever you plug in for the k or the x, you're going to get a value. Okay, the next part, called the comparison test. This is called the limit comparison test. They refer to it in the book as the LCT. You're going to suppose that A sub n is greater than 0 and B sub n is greater than 0 for all your n's. So here are the 3 incidences for the comparison test. If the limit as n approaches infinity, if an and you compare it to bn equals some c value, and 0, which is less than c, which is less than infinity, then both an and bn will either both converge or they'll both diverge. If the limit as n approaches infinity of an over bn equals 0, then bn converges, then also an must converge. And the third thing is, if the limit as n approaches infinity of an divided by bn equals infinity, well, I think you know if it equals infinity, then if bn diverges, then an diverges. So, just to give you some examples, determine if the series converges or diverges. And here it is. And I'll probably give you 3 examples. These 3 are in the book also. Here's the first one, A. It goes 3/4 plus 5/9 plus 7/16 plus ... plus, and here's what the formula is for the series. The formula is n equals 1 to infinity of 2n plus 1 over n plus 1 squared. So, I'm going to compare this to a more simpler series. I'm going to compare this. I'm going to take more of a basic equation to compare this. And this is where they got the basic equation. In your book too, this is in your book under the comparison test under 10.4. I mean 10.5, sorry. So, how do they get a more basic one? So basically, they take 2n plus 1, and they expand the n plus 1 out, and they get n squared plus 2n plus 1. And that's from over here. So basically, you take the largest value in the numerator and divide it by the largest in the denominator, and that's called your end behavior, if you remember doing this. It's been a while since you've done this. But the more basic formula that we're going to use is this one. I'm going to circle it. So, I'm going to compare this with the other one. So this is what you're going to do. You're going to take the limit as n approaches infinity, and the original one is 2n plus 1 over n plus 1 squared, and you're going to divide it by the more basic one, 2n. You put the original one on the top and the more basic one on the bottom, which is equal to 2n plus 1 over n plus 1 squared times, you flip this to n over 2, which is equal to 2n plus 1 over n squared plus 2n plus 1 times n over 2, which turns out to be distributive property, I'm going to 4n plus, not 4n, start again, n times 2n is 2n squared plus 1n all over 2n squared plus 4n plus 2 as the limit as n approaches infinity. Okay, we're going to go back into our limit formula. I'm going to do L'Hopital's rule, and I'm just going to take the derivative of the top, which is 4n plus 1, and I'm going to take the derivative of the bottom, which is what, 4n plus 4. And you can keep continuing this and you're going to get 1. So it converges. I can, again, take the derivative of that and get 4, and over 4 makes 1. That's how I got 1. The book uses 1 over n. I use 2 over n. It still converges. It doesn't matter if you use 1 over n or 2 over n. Okay, I'm going to do another one. I'm going to do 1 plus 1/3 plus 1/7 plus 1/15 plus dot 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 plus, here's my series, n equals 1 to infinity of 1 over 2n minus 1. So I'm going to find the limit as n approaches infinity, and I'm going to put my original one on the top, and I'm going to put my more basic one on the bottom. And my most basic one for that one would be 1 over 2 to the n. And then I do the limit as n approaches infinity of 1 over 2 to the nth minus 1 times 2 to the nth over 1, which turns out to be the limit as n approaches infinity of 2n over 2n minus 1, which turns out to be the limit as n approaches infinity. I'm going to multiply the top and the bottom by 2 to the negative n and 2 to the negative n, which will make 2 to the 0 up there, and this one's going to make 2 to the 0 minus 1, 2 to the 0 times 2 to the negative n, which turns out to be 1, which turns out to be 1. So the limit as n approaches infinity of 1 over 1 minus 2 to the negative n is 1 over 2 to the n. And as n is getting bigger and bigger and bigger, this is getting closer and closer to 0, so 1 divided by 1 is 1. This also converges. The reason why I multiplied by 2 to the negative n is so that I could simplify both of these. Another way I could have done, I didn't even think of this, I could have divided everything by 2 to the nth, and that would have done the same thing. I've got one more, and here's my last one. 8/4 plus 11/21 plus 14/56 plus dot dot dot, and here's my formula. N equals 2 to infinity of 3n plus 2 over n cubed minus 2n. So I'm going to find the limit as n approaches infinity. I'm going to put the original on the top, and I'm going to put the more basic problem on the bottom. What's the more basic problem is this. Take the highest power in the denominator and divide it by the highest power in the numerator, which ends up being just 3 over n squared. You can either use 3 over n squared. I think the book uses 1 over n squared. That's even more basic than 3. Back here too, where was it? Right here. I guess we got one more, right here. I used n over 2. I think the book used 1 over n. So just keep that in mind. A little bit more basic one than 2 over n is 1 over n. Okay, so come over here and finish this. Divide it by 1 over n squared. This is the limit as n approaches infinity of 3n plus 2 over n cubed minus 2n times n squared over 1, which gives me the limit as n approaches infinity of 3n cubed plus 2n squared all over n cubed minus 2n, which gives you the limit as n approaches infinity. L'Hopital's rule, take the derivative of that, 9 n squared, take the derivative of that. 4n, take the derivative of that. 3n squared minus 2. Or take the highest power in the numerator and divide it by the highest power in the denominator. Whichever way you do it, you still get 3. In order to find the limit as n approaches infinity, you learned this a long time ago. You would have learned it in way back in probably chapter 2. You take the highest power in the numerator and divide it by the highest power in the denominator. And it also converges. Okay, I have just a few more things to talk about. I need to talk about the alternate series test. For example, if you have some series n equals 1 to infinity, and you have this a negative 1 to the n plus 1 times some, whatever this is, what's going to happen is every time it's going to keep going positive, negative, positive, negative, and so on. So if you have an alternate series, this needs to be true. Each of the UNs need to be positive. UN, which is like the first term, needs to be greater than or equal to the next term after the first term. So this is like the first term, and this is like the second term. So the first term needs to be greater than or equal to the second term. And the limit as n approaches infinity of UN must get closer and closer and closer to 0. All of these must work. In order for your series to converge. All of these must work in order for your series to converge. And then they talk about alternating series estimation theorem. So, if you have a series of n equals 1 to infinity of a negative 1 to the n plus 1 un, this little part will change it from positive to negative and negative to positive. It just says that it satisfies the AST, which is up above, the alternating series test. Then the error for the nth partial sum is less than the next term and has the same sign as the first. Remember, this is always the second one, and then they're talking about the first. A couple of more terms to go through. I've just got a couple of more things. Absolute convergence. If you have some series and it converges absolutely, it just says that the series AN is equal to the series BN if B1, B2, and B3 has any arrangement. Then it also converges. They both are going to converge. Oh, here's a weird one. Conditional convergence. If some series converges, you can rearrange its terms to form a divergent series. It's kind of interesting, isn't it? If some series converges, you can rearrange it so it's in a order so that it can converge. Okay, last part, how do you test a power series? And here's the power series. N equals 0 from infinity. Sum A, let's call it A and x minus A to the n. Here's your power series all the way back to the beginning for convergence. How do you test for convergence? Here's some things. You can use the ratio test, like we did in the last section. Number 2, if the interval is finite, you can test for convergence at the endpoints. If the ratio test fails, if this fails, you can try the comparison test. Okay, the last thing, the interval of absolute convergence says it diverges. Okay, so I want you to open up your books on page 526. I'm going to wait for you to open up your books to page 526. Okay, if you open up your books to page 526, I'm just going to go over that flow chart with you. Procedure for determining convergence. So let's just kind of go through this kind of here. The nth term test. Is the limit of some series equal to 0? If it is, you can keep going farther. If it's not, then you can diverge. You can use the geometric series test. You can use the PSeries test. And you can just keep reading these flow charts. Geometric series test, remember you have to check the ratio. Is the ratio less than 1 or is the ratio greater than 1? This kind of just ties everything that we've learned. The geometric test, now look over to the right, and what you are doing, there's a formula. If it converges, in fact, I'm teaching it right now in Algebra 2. The formula is A1 over 1 minus R. That A stands for the first term. First term over 1 minus R. If R is less than 1, you can find the answer. If the ratio is greater than 1, then you cannot find the answer. Does the series have the form 1 over NP? If it does, then the series converges if P is greater than 1, and it diverges if P is less than 1. The next one, does the absolute value converge? Apply one of the comparison tests, like the integral test or the ratio test or the nth root test. The alternating series, Is there any integer n such that u of n is greater than or equal to un plus 1? Okay, I was just going to maybe go over a couple of these. I'm just going to show you just really quickly. I don't know if I'm going to do all of them, but I'm just going to give you the geometric series test. All you're going to do is, for example, I'll just give you one from geometry. I'll give you, let's go 16 plus 4 plus 1 plus 1 4 plus dot dot dot. And I will give you the formula for it. The formula is 16 times r to the n minus 1 power. Oops, 16 times 1/4 to the n minus 1 power. So, this is called the geometric series test. We did this a while ago, but all you do is you find your r, and your r is 1/4. You can tell by looking at it that it goes down by 1/4. And is r less than 1? Yes. So then I can use my formula. My first term is 16 over 1 minus my ratio, which is 1 minus 1/4. So it's 16 over 3/4. And that's going to give me 16 times 4 over 3, which is 64 thirds, which is 20 point something. It's going to converge to 20 point something. This is called a geometric series test. 1 plus 2 plus 4 plus something. As you can see, then it going up by times 2. The ratio, absolute value of r, is greater than 2. Since that is greater than 1, it doesn't converge, but it diverges. So what I just did was, in this flow chart, I just gave you an example of the geometric series test. On the P-series test, I'll give you an example. If you have some series, let's just say n equals 1 to infinity, and you have 1 over n, and let's make this the p. I'm just following it. If p is greater than 1, your series is going to converge. If your p is less than 1, your series is going to diverge. So, for example, n equals 1 to infinity, and let's make 1 over n to the second. Let's try that. Okay, so when I bring this out, I'm going to let n equal 1, I'm going to get 1. When n equals 2, I'm going to get 1 over 4. When n equals 3, I'm going to get 1/8. Since p is greater than 1, you can see that these numbers are getting smaller and smaller, and they're going up by a half. Not by a half. They're going up by 1/4. You know what I mean. They're going up by 1 over n squared. And you can see that these are getting smaller and smaller, and they're converging. I'm going to switch it up. I'm going to do the same thing. N equals 1 to infinity, 1 over n, but let p be less than 1. So let's say my p is a -1. So this is going to end up flipping it to just to an n. And as you can see, n is 1, n is 2. You're going to get 1 plus 2 plus 3. These numbers are just getting bigger and bigger, so there's divergence. So, basically, I just gave you examples of the geometric series test and the P-series test. If your series is non-negative, you can converge it by doing the comparison test. I just did the comparison test with you, the integral test or the ratio test or the nth root test. Those are all examples on exercise 73. So if you want to look over exercise 73 on how to do the test for those, you can. So again, this is a very hard section. Basically, you're just trying to figure out if the series is converging or diverging by using different tests.